Hi, welcome to the presentation. Solar geoengineering is up to 14 times more efficient than carbon dioxide removal. Issues in climate forcing and governance. I'm Dr. Alec Feinberg from DFR Soft. My background is originally from Northeastern University. Thank you for listening to the presentation. And let's get started. This talk is based on the following preprint that's been submitted. And has the same title, and you can get the full paper on ResearchGate. So we're providing an overview for that paper. So let's look at it. Introduction is broken down into two parts. There's a forcing model, so that's part one. We're going to overview that model, we'll look at the results, and make comparisons to AR6. Then we're going to talk about mitigation and forcing efficiency estimates. So we're going to do solar geoengineering versus greenhouse gas removal, solar forcing versus greenhouse gas efficiency. So, okay, we're going to start off with the linear forcing model. So the idea is we're going to look at the natural climate system, the pre-industrial estimate for the Earth's energy budget. We're going to use that model because energy adds linearly. And so basically what we're saying is what happened in the pre-industrial and the system, and then we perturb it. There's a small perturbation, about 1.2%. So we're going to look at that perturbation using the natural system. We're going to say, well, let's just assume that things add linearly. So how much more, if we add this much more greenhouse gas, what will occur? So let's look into that. We're going to start with the Earth's energy budget. So this is basically a pre-industrial. I call it. I happen to be using 1950 at the time, which was close to that. This comes from this paper here, a re-radiation model, and it's basically energy trapping. So about 340 watts per meter squared comes in. About 100 watts gets reflected from the planet's natural albedo, and we absorb about 240 watts per meter squared. And then of that 240, we trap or re-radiate or amplify. One can think of it as amplifying because we're actually increasing the energy to the surface from the greenhouse gases. So it must be about 147 in order to get to 384, which would be our comfortable 15 degrees centigrade. So we know this can't be the number. This is the actual number. So that's additive, and we see how things nicely add. And this is an iterative diagram. It's repetitive, and the actual exact solution is 61.8 for the amplification factor. So it's a pretty interesting model, and you can take a look at that from this preprint, from this actually published paper. All right. So the forcing method, we're using really an unsaturated linear forcing tool. It's a steady state physics-based model. Each spectral unit of greenhouse gas, we're going to treat it as equal thermodynamic forcing potential. So it's a linear amplification, no feedback kind of model designed to provide upper bound. Now, please realize this is a diagnostic kind of tool, so it's not a circulation complex model. We don't claim that to be the case. We're just saying it's a diagnostic tool providing first order feedback-free forcing estimates, upper bound kind of thing, based on the natural climate system. So let's start off with carbon dioxide using the model. So we said that the greenhouse gases add 62% more energy to the surface than solar provides. This effect may be treated as an amplification effect in the linear model with the 238 watts per meter squared that's absorbed by the sun. So we get 148. So you can see the amplification if you multiply the 238 times 0.62. That gives you the 148 increase, and there it is right here, 62%. Now, of the 62% greenhouse gas effect, 19% of it is related to CO2. So that's from one of the references in my paper. So that's an important number. So if we take 19% of the 148, we're going to get 28 watts per meter squared. So CO2 effectively contributes 28 watts per meter squared to the natural greenhouse gas effect. Now, let's say we add more CO2 to the atmosphere. So the Earth's natural greenhouse gas 148, CO2 19%, that comes out to 28 watts. Now we're going to perturb the system from the pre-industrial, which was about 280 parts per million of CO2. Then the linear model, we're going to increase that to 410. So we're literally doing that. So we take this ratio of 410 to the 280, and we end up with an increase of 41 watts per meter squared for the CO2 effect. And so the difference for the 41 from the 28 for the natural system means that we increased about 13 watts per meter squared. Okay, now we need to make an estimate to figure out how much warming does that cause on the surface. We know it can't be the whole 28. I mean, it can't be the whole 13 watts per meter squared. So that has to be scaling how much warming are we actually causing. So for the 28 watts out of the 238, for every 28 watts we would get of the 238, we would get about 0.118 watts. So this is the scaling ratio of what we would actually get for the 28 watts for that. So that for every watt per meter squared, about 0.118 gets to actually a warming potential. So the scaling factor, so it's a scaling factor for the CO2 pre-industrial contribution of the 28 to the greenhouse gas absorbs for the flux to the 238. So in the unsaturated linear model, the 13 watts times the 0.118 scaling factor says that the forcing would be 1.54 watts per meter squared. So that's really the crux of the model. And I did that for all the greenhouse gases. So I have this particular model, and this is the way it comes out for that. So we can look at the model. The F factor for each particular greenhouse gas is different. So the CO2 is 3.3, which we just saw, which comes out if you multiply the 3.3 times the difference in the pre-industrial versus the 410 minus 1 factor, you would get this 1.54 over here. So that you put those two C's in there. And the same thing for methane. You come up with a 0.228 watts per meter squared forcing, and so forth. So that's what I got from this particular model. Just taking a look at the two different models. This is the saturated model by Meyer, 1998. You can see though it's a log saturated model. So for every as in the saturated model, it you would expect less forcing as the concentration goes up, where in the linear model it just goes up linearly. So this is really an upper bound. It's not, again, it's a diagnostic tool, so don't take it for an absolute. But in general, it provides an upper bound and gives us an idea of what's going on. And notice that the 2 times CO2 upper bound is 3.3, where in the saturated model it comes out to 3.7. So this is saying this should be the upper bound, and we're getting more in the IPCC. So let's actually look at the IPCC and make a comparison. So this is the full chart, and this is the forcing that I found for the CO2, and this is what the AR6 is saying, 2.16. So that's about a 29% discrepancy. And then we also looked at the 2 times CO2 model. So it gives us 3.3 versus the Meyer model, which is 3.7 for the saturated, and that's about 11%. And methane came out to be about a 58% discrepancy. So those are the other discrepancies. So the total watts per meter squared forcing came out to 2 watts per meter squared, where the AR6 comes out to 3.26. Now we have some justification for the model, so we're going to look at that. Notice also I was able to come up with a global warming potential for each greenhouse gas. And notice that the methane is pretty much in line with the AR6, which says it should be about 80 times more global warming potential than CO2. All right, so let's look at the key results that we have here. Keep moving it on. Um, the the unsaturated linear forcing model shows a 39% discrepancy for the upper bound as a diagnostic tool to the AR6 central values. In this time period, we're looking at 2019 values versus the pre-industrial time. The CO2 estimate is about 30% discrepancy for the upper bound. The doubling is about 11%. And as I mentioned, this is diagnostic, unsaturated linear forcing model. It reveals potential over estimates in the AR6 forcing. And how do we justify that? Well, we noticed that there's a very large planetary albedo decline this would provide more room because we noticed that there's a discrepancy of about 1.26 watts here between the 2 and the 3.26. So maybe that's related to the planetary decline in the albedo that may be going on. Now, some assurance for the diagnostic model. As I mentioned, the global warming potentials were somewhat in line with the AR6, especially for CH4. The 2019 forcing values is about 5 watts per meter squared. When you add feedback, so I said forcing, so it should be forcing plus feedback. Out of the 386 is a perturbation of about 1.2%. So this suggests about a 98% of the energy balance remains intact. So it gives some credence to um, the linear model because it's showing we don't really have that large, we're 98% intact, so it should be reasonably okay to make such estimates. Now, keep in mind that we're feedback free, but I do talk about feedback in my paper. And keep in mind that cooling is cooling, so whether you do it for CO2 or whether you do it for solar, and in fact, solar uh, feedback happens a lot faster. You get snow and ice melting a lot faster. So then, when you add natural greenhouse gases, so we don't expect that things would be worse with the model. So if you were to incorporate feedback, that the comparison would be any less. All right. Attribution considerations, as I mentioned, highlight the divergence or the convergence model. There's been an observed albedo decline of about 0.5% since 1998, and that would be a maximum value of about 1.7 watts per meter squared, and that's not considered in the AR6. So maybe there's some interesting help here for that. In 2023, the energy imbalance nearly um, there's a some some this paper points out about the energy imbalance issues and relates it to the albedo decline. So that's a very important paper. Cloud aerosol uncertainties remain. I also talk about urbanization increases from dark surfaces, which also contributes to somewhat the albedo decline. All right, so we're going to move on now, part two. So we'll get into some of those other issues. So this is a different kind of similar idea, using the same fairly similar structure, mitigation comparison. Um, uh, so solar geoengineering versus CO2 removal. All right, so let's look at that. If we talk about, say, 1 watt per meter squared heating a surface, that's if solar comes in. If we heat a surface 1 watt per meter squared, now uh, of that we get a greenhouse gas effect. We set a 62% amplification. So the actual full effect is that when solar forcing for per watt per meter squared is actually ends up being about a 1.62 watt per meter squared increase. So if you were to cool the surface and you had a very good reflective surface, uh, instead of that hot spot, you would get about a 1.62 watt per meter squared cooling, even though the surface was originally only contributed 1 watt per meter squared. All right, now the difference is that if you cooled by CO2, if you just take out the CO2, that's not really going to change the greenhouse gas re-radiation or trapping that much. It's a 0.19 effect times the 0.62. So that's what happens. So let's look at that a little more closely. Um, and as we a little more closely that go through that. So let's look at the cooling efficiency. Solar geoengineering cooling. Um, we talked about that. We're going to cool the surface by 1 watt. Plus, we get an additional cooling because we're not getting the greenhouse gas effect from the energy release, the IR energy released from that surface. So again, this is a surface model. This is not what's happening at the top of the atmosphere. So another kind of discrepancy on that. But it's a diagnostic tool. So the cooling from carbon dioxide removal, we get again, we would have for every watt per meter squared, we only get 0.19 out of the 62, so the contribution is 0.118, and we saw this factor before. So now we talk about solar geoengineering cooling per watt per meter squared would be 1.62 versus the carbon dioxide removal would be 0.1178. It comes out to, and that gives us a factor of 3.75 number. Okay, so there's the difference. So I make a summary. This is the area right here where I just talked about. There's the 13.75, 13.8 factor, and I added some perturbation for the perturbation effect. That could go as low as, say, 12.6 for the upper bound. So I did that, and there's a number of ways to write the efficiency. So that's all this other stuff is. For example, the efficiency of carbon dioxide removal compared to solar geoengineering is 7.3%. So there's different upper bounds for that. And then also, for general greenhouse gas removal, the factor instead of 13.8 would be 2.6. So that's in the paper if you're interested in that. And we talk about the amplification effect and and things of that nature. So this is just a summary of the upper bound comparative estimates. Again, this is a diagnostic tool, provides upper bounds. Governance implications. Solar geoengineering should be considered as a premier mitigation tool. Urban albedo management, dark roads, roofs, vehicles, building sites, dark building sites remain underregulated. The Paris Accord should be expanded to explicitly include albedo goals. A lot of urbanization authors have requested that, and the Arctic albedo protection is especially urgent. We have to be very careful because albedo forcing, you can turn these things around. I didn't do that in this presentation, but also the forcing, solar forcing is also 13.8 times uh, higher higher efficiency than carbon dioxide forcing. So keep that in mind. So we really need to protect albedo. Protection is important. And so that's All these are very important considerations for governance. I mentioned dark surfaces. I'm a big, it's a part of my theme. I actually have a website called Dark Ban Black Roads, and it talks about other things. .com or .org, I think. And you can see black surfaces. I'm very upset about that, and we should not be. It's very bad behavior to do that. A lot of people don't find that this contributes much, but it does. I talk about recent papers that find that urbanization effect is about a 12.8%, unlike satellite findings. And I talk about some of the challenges of satellite findings, unable to measure tall buildings, and vertical structures, which most of the city, believe it or not, the surface area is building sides is tremendous amount of surface area, and they have problems with ERF estimates. So the ground-based measurements that the model that I quoted, I mean the not only the modeling but also the measurements that were done by author Zhang and all, quoted in my paper, finds discrepancies, and that urbanization we should not be doing these kinds of things. It's bad behavior. So the conclusion is that solar geoengineering is 14 times more efficient than carbon dioxide removal on an equivalent energy rate basis. Um, Again, it's also the Earth responds more strongly to shortwave reflection rather than the long wave absorption. The planetary albedo decline is an overlooked factor in warming. Governance framework must address these things explicitly. Um, I make a part kind of a theme of mine. I wrote a paper called Annual Solar Geoengineering, and I talk about the pathways in another paper. And so I believe it's important. Let me talk a little bit about that. Uh, because a lot of people are worried about circulation issues, so I came up with annual solar geoengineering. And in general, annual solar geoengineering, we reduce solar geoengineering just yearly to stop the yearly increases. That gives us time to address the albedo issues and the carbon dioxide issues. So we're not trying to reverse all of global warming and cause and less circulation concerns. It's better for governance. The yearly increases before 2019 was about 0.02 versus a 1 degree increase, and you can see it's a factor of 50 reduced. So it's less effort to do that, and the approach it's more feasible. It's a more feasible option, better for political and governance. It's 50 times less solar area. It's low. Leads to a smaller in the annual solar by about a 50x portion smaller uh, issues. Um, so it's a better plan, and I I provide a full plan here with multi methods for doing mitigation for using solar geoengineering, which we must do because of the addiction to fossil fuels right now. And we have urbanization, earth brightening is in a combination of hotspot earth brightening, also space sun shading. I talk about that and I show that it's much more feasible than other people have estimated. Um, their estimates of 2 times the size of India was way overestimated, and I provide the actual uh, physics for that in my annual paper. Um, and that's way overestimated. It's much more feasible, especially with annual approach. And the Antarctic and the Arctic stratosphere aerosol injection should be an important player. All methods are important. So that's basically my talk, and I hope you enjoyed that. And thank you for listening. Okay.